Hello. My name, as I've been very kindly introduced, is Anna Pajajski. If you're wondering about the spelling of that, the answer is 96 if it's on a triple word score. I'm here to talk to you about the future of materials because I'm a materials scientist. Give me a cheer if you've heard of materials science. Okay, don't worry, that usually happens. Materials scientists, we look at stuff. And that can be any kind of stuff, right? The material that makes up this carpet, the foam in the seats that you're sitting on, the components in these lights. And we zoom in to see what the atoms are doing inside those materials. And usually these atoms can tell us what a material's properties are going to be. So that might be its hardness, or its flexibility, or its sharpness. My mum is convinced that I just play rock, paper, scissors for a living all day. And that is kind of true. But today I'm going to be talking to you about the future of materials, specifically smart materials. Now, one of the most exciting applications of smart materials that I've ever come across is the pine cone. Now, that doesn't seem very smart, you might say, but the pine cone is a remarkable example of a smart material because it's made of a material called a hygroscopic material. Now, this is a material that absorbs moisture, and when it does that, it changes shape, it expands. And pine trees have gone through years of evolution, and they've worked out that the best weather to plant a new pine tree is when it's hot and dry. Right, when it's cold and wet, pine trees just don't like to grow, apparently. So the pine trees have developed these pine cones with this hygroscopic material, which means that when it's hot and dry, and it's lovely weather for planting new pine trees, the pine cone is opened out and the seeds can disperse. When it's cold and wet, then this hygroscopic material expands, and that causes the spines on the edge of the pine cone to close up, and the seeds can't get out. So pine cones are a remarkable example of what we call an actuating smart material, a smart material that moves in response to something. So the definition then of a smart material is an object that has a property like its color or its shape or maybe its magnetism. And this property changes in response to an external stimulus, which might be light levels or moisture levels, as in the case of the pine cone, temperature, pressure, that sort of thing. What I'm going to be talking to you about today is some futuristic examples of smart materials. So actuators are just one example. There are other categories of smart materials as well. Color-changing materials, materials that can sense, heating and cooling materials, self-healing materials, and phase-changing, which means freezing and melting. And this all sounds very futuristic. I've told you I'm talking about the future. But actually, smart materials have been around for a very long time. These are the pyramids of Giza. They were built 4,500 years ago. And actually, the lime mortar, the cement material that makes up these pyramids, is actually self-healing. So when a crack develops in this material, it can heal itself without any kind of human interaction. But the first material to be recognized as a smart material came in 1880, and it looks like this. This is quartz, and a remarkable property was discovered by the much less successful and famous husband and brother-in-law to the only scientist ever to have won 2 Nobel Prizes in 2 different subjects. Who am I talking about? Shout it out. Anybody? Marie Curie, exactly. The Curie brothers, they discovered that quartz has a remarkable property called piezoelectricity. What this means is that when you squash a quartz crystal, the Curie brothers discovered that a voltage is set up across it. And a year later, they discovered that the opposite was true as well. If you put a voltage across a quartz crystal, then the material itself physically deforms. Now, to understand how materials do this, we need to zoom in and see what the atoms are doing. So, TEDx, are you ready to do some material science with me? Yes! Thank you for your enthusiasm. So, let's see what the atoms are doing. Now, to work out what quartz crystals are doing, the clue's kind of in the name, actually, crystals, right? To most people, crystals, the word crystals it draws up an image not too dissimilar to this one, actually, kind of glistening, transparent gemstones. But actually, to a materials scientist, crystals are any materials in which the atoms are all lined up in neat little rows. So metals are mostly crystals, ceramics, some plastics, ice, rocks. All of these materials, for me, are crystals, okay? And the smallest element of that crystal is called the unit cell. And it's basically just the small repeating unit that goes over and over again in order to make up this very orderly atomic structure. And in most crystals, the unit cell is symmetrical, so it looks the same back to front, upside down. But in a piezoelectric material, the unit cell is not symmetrical, it's asymmetrical. And that doesn't sound very remarkable, but it has this amazing effect. Because ordinarily, in a quartz unit cell, you've got a positive atom next to a negative atom, and these charges just cancel out, usually. But if you squash the unit cell, or if you stretch it, then these atoms move a bit, and that means that the asymmetry means that the positive and the negative can't now cancel out. So what you end up with is a unit cell that is slightly positive on one side and slightly negative on the other. And these charges, they're not particularly strong. We're talking about electrons here. But if you multiply this effect across the many, many millions of unit cells in a quartz crystal, then what you end up with is a measurable electric voltage. So these are materials that generate electricity if you squash them. And you'll be familiar with some other materials, smart materials as well. For example, the photochromic sunglasses that go dark when you go outside. Those Duracell batteries that show you how much charge is left in the battery when you cover it up. Color-changing mugs and mood rings. You guys know what mood rings are, right? Young people in the room? Yeah, mood rings? Okay, not just me. These are all examples of smart materials that you'll know today, but one thing you'll notice is that they're all quite naff, right? Like, I've been talking about amazing smart materials, but these are not particularly that groundbreaking. And I'm going to come back to the reason why we don't have such groundbreaking smart materials around at the moment. But an example of a futuristic application of smart materials I wanted to speak about today looks like this. Okay, hang on, that doesn't actually look that futuristic, does it? That's because it's not, actually. This was drawn in 1488 by Leonardo da Vinci. This is Leonardo da Vinci's flying machine, which he invented. And he invented it having been observing the flight of birds and bats and the wing shapes, because he recognized that, again, birds and bats and flying animals have had millions and millions of years of evolution in order to inform their design of wings to make the best and most efficient wing design. So Da Vinci, he designed his flying machine by copying the birds and the bats. And these wings were flexible, they were jointed, they could change shape a lot in response to the live flight conditions that the machine found itself in. But if you compare this flying machine to the wings of the planes that we all fly around in now, they're quite different, aren't they? Our planes have wings that are fixed. Okay, there's a few stiffly movable parts, but really, they're quite rigid. And I'm sorry to tell you, but these wings are not the best wings for flying, even though we all fly around with them all the time. The best wings for flying, in fact, are wings that can change shape. They can move in response to what the flight conditions are doing. So in the future, our aircraft are going to look much more like Da Vinci's design than our current fixed wings design, and that's all going to be thanks to smart materials. So what materials then are we going to use? Well, in Da Vinci's design, he had a hard jointed pieces of wood, quite a lightweight material, and then he stretched over it to mimic the skin of the animal. He stretched over it a piece of silk. So in our smart aircraft, we're going to have the rigid component is going to be made of a shape memory alloy. This is a metal, and it actually remembers the shape that it was in before it got moved into a different shape. So with our shape memory alloys, we can change the shape of the wing simply by heating these materials up. The skin of the aircraft is going to have to be then both hard and rigid and strong to withstand the aerodynamic forces in flight. But it's also going to have to be flexible in order to be able to withstand the changing shape of the wing underneath. And smart materials are going to allow us to be able to do this. Shape-changing materials like electroactive polymers and shape memory polymers are going to be able to be strong and stiff at times, but then soft and flexible at times as well, just either by being heated up or by having an electric current flowing through them. And I call this a skin of the aircraft, and actually it's going to be more like skin than perhaps you realise, because again, with the piezoelectric crystals, which we met earlier, or some quite slightly more exotic sounding quantum tunneling composites, these materials will be able to allow our aircraft to sense, to be able to feel things, because these materials produce a measurable electric voltage when they are pressed. And finally, again, it's going to be more like a skin than our current designs, because these materials could be made to be self-healing. Just like those pyramids of Giza were self-healing, you can actually get plastics now which are able to heal themselves without any kind of human interaction. So if your plane happens to get a hole in it, that's no problem even when you're in the air. So these are some really cool examples of smart materials, but all the ones that I've spoken about just now actually exist already. Right? You can buy them, most of them, on the internet. You can work with them, you can play with them. So why then do we not have Da Vinci's aircraft working today? Well, that's because smart materials, unfortunately, have quite a few problems. They're slow to react. So if you wanted to change the shape of your wing, it might not change as quickly as you like. Some of them are too delicate or unstable to use. Their performance can diminish over time, which again is not something you really want to hear if your aircraft is made out of it. Sometimes incorporating them into working devices can be quite difficult. The switch threshold can be difficult to control, so the temperature at which it changes or the pressure at which it changes can be difficult to control. Some of them are too toxic, some of them are too expensive, and some of them are just too difficult to make enough of them in order to make something useful. But the point that I want to end on is that these problems are not too difficult to solve, right? And material scientists and engineers are going to be working on these problems, and you guys are hopefully the material scientists and engineers of the future that can solve these problems. So I hope you'll accept this challenge of joining me in material science and engineering and working on smart materials, because they deserve a place in the future, and it's going to make the future a very exciting place to be. Thank you very much for listening. I've been Anna Pajajski.